Good morning. The hearing will come to order. I want to welcome our guests. Without objection, the chair is authorized to declare recess at any time. And before I want to deliver my opening remarks, I want to note that today the committee is meeting both in person and virtually. And I want to announce a couple of reminders to members about the conduct of this hearing. First, members and staff who are attending in person may choose to be masked, but it is not required. And however, if any individual's symptoms, a positive test, or exposure to someone with COVID-19 should wear a mask while present. Members who are attending virtually should keep their video feed on as long as they're present in the hearing, and members are responsible for their own microphones. Please also keep your microphones muted unless you're speaking. And if members have documents they wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing. Also like to note that Subcommittee Chair Suzanne Bonamici is asked to wave onto the elite exclusive space subcommittee for this meeting. And without objection, she is waved on. And if there are other members who so desire, we'll recognize that at the time. And before we start, I just wanted to take a moment to recognize the thrilling first successful test launch of the Integrated Space Launch System and the Orion crew vehicle, Artemis 1. Very, very exciting. First time in 50 years. Cape Canaveral at 1:47 this morning. This is a momentous achievement for NASA, for Democrats, for Republicans, for the nation, for the world. It's a huge step forward into Mars. So on the behalf of my colleague, Dr. Babin, and all of our members of the Space Subcommittee, I want to congratulate all those at NASA and its industry and international partners on this historic Artemis 1 launch that will send Orion on a test flight journey to the moon and back. Now, we get to turn to another thrilling success. Good morning and welcome to today's hearing on Unfolding the Universe, initial science results from the James Webb Space Telescope. I want to welcome our esteemed panel of witnesses. We are so pleased that you're joining us today, and you're joining us in person, which is a rarity in the last 2.5 years. So very exciting. Most of us are here in person. Watching online have seen the awe-inspiring images that James Webb Space Telescope has. The Tarantula Nebula, the Cartwheel Galaxy, the Cosmic Cliffs, Stephan's Quintet, just to name a few. The visual impact of JWST's images alone, with the unprecedented clarity and detail, provides an inspirational value that I hope will draw a new generation of scientists and explorers into astronomy, astrophysics, and the sciences. Today's hearing will delve into what those stunning images tell us. What questions will those mesmerizing pictures answer? What new mysteries will they help reveal? And how will JWST's observations help us understand how our universe came to be? The birth and evolution of stars, planets, galaxies, how the conditions arose for life to exist on this planet, maybe in the solar system and in this galaxy. I'm really eager to hear from our witnesses on what they're learning in just the first few months of JWST's science operations, which began officially July 12, 2022. Because the science is just in the beginning, but the journey to get here has been decades in the making. Recommended as the top priority for major new investments in the National Academies of Science, Engineering, and Medicine's 2000 decadal survey, this is 22 years ago, for astronomy and astrophysics. JWST's design, development, integration, and testing on the ground spanned more than 20 years and required 10 technology miracles along the way. Challenges were many. Success was never a guarantee. Even following its successful launch on the Ariane 5 rocket, the telescope's complex deployment sequence over 29 days involved 344 potential single-point failures. So I think we're all very proud of the dedication and commitment of the many scientists, engineers, international partners, contractors that brought us here to celebrate the first science of JWST, the most powerful and complex telescope humans have ever sent into space. And while the initial results and first imagery have been nothing short of awesome, I'm confident there's much more to come, and much more than we can even imagine. So thank you for being here in person for what I predict will be a fascinating discussion. And let me now recognize my friend, Dr. Babin, for an opening statement.
Thank you very much, Mr. Chairman. I appreciate this opportunity to be able to hear from you expert witnesses about this fantastic project. But good morning. I want to welcome you witnesses here before us today, and also I would like to mention the successful launch of Artemis 1 early this morning. Once again, our nation has captured the world's attention by venturing back to the moon with the pursuit of going even further where no one has ever gone before. Our successful launch of Artemis 1 is a remarkable feat made possible by so many brilliant minds across this great land of ours, including hardworking men and women at Johnson Space Center, which I am very privileged to represent. As a longtime supporter of the Artemis program, I want to congratulate everyone involved in this launch and wish them a successful mission. But now back to another fantastic achievement. The James Webb Space Telescope, also known as JWST, finally launched last Christmas morning with great fanfare. The flagship mission is the culmination of over 2 decades of very hard work and $10 billion in taxpayer investment. The successful development, launch, and deployment of JWST is a testament to the engineers, the scientists, and the technicians who are so committed to this great project. NASA and its contractors once again demonstrated that the impossible is within reach. JWST also shows that the U.S. is still capable of building and operating large-scale, highly technical systems. This fact cannot be overstated. And while it's great to take a victory lap with the successful checkout of JWST systems, we must also be vigilant in maintaining this capability in the future. We can't take for granted that we will be able to build cutting-edge systems in the future just because we were able to do so in the past. It will require ongoing congressional support and oversight to maintain key capabilities to build these world-class systems. This is imperative not only for our scientific leadership, but also our national and economic security, as the dual-use nature of space impacts our citizens' lives every single day. Just as with the Hubble Space Telescope and NASA's other great observatories, we expect great things. JWST was touted as potentially rewriting the textbooks. And as breathtaking images and results have come in from JWST over the last 4 months, we are finally starting to see the fruits of our hard labor. Today's hearing is an opportunity to review these findings and to think about the future. With the spacecraft operating and providing data, what are the lessons learned from JWST that can be applied to future missions like the Nancy Grace Roman Space Telescope or future follow-on observatories? How can Congress help ensure that those lessons learned are implemented and followed through? Because the last thing we want to do is to make the same mistakes twice. Cost overruns and schedule delays have real-world impacts. They delay the start of other new and exciting missions and sometimes prevent them from even starting. The recent example of the Psyche mission comes to mind. Developed under the cost cap discovery program in NASA's Planetary Science Division, Psyche missed its planned launch date earlier this year and will not launch before next October. This will result in the program exceeding its cost cap and delaying the next Discovery-class mission, Veritas, by at least 3 years. It also raises the question of whether Discovery missions really have a cost cap or whether the caps are just recommendations. A recent Discovery mission, InSight, also exceeded its cost cap after issues with the partner-provided instrument resulted in a missed launch window to Mars. The moral hazard caused by specifying a cost cap but not holding missions accountable to that cap is directly applicable to how NASA will manage future astronomy missions after JWST. These are all issues that we need to remain focused on going forward, but today I am very interested in hearing from our expert panel on some of the more interesting results that we have derived from JWST's first year. And I look forward to their testimony, and I yield back the balance of my time, Mr. Chairman. Thank you.
Thank you, Congressman, very much.
Sir.
At this time, I'd like to introduce the witnesses. Dr. Mark Clampin is the Astrophysics Division Director in the Science Mission Directorate at NASA headquarters in Washington. Previously, Dr. Clampin was the Director of the Sciences and Exploration Directorate at the Goddard Space Flight Center. At Goddard, he also previously served as the JWST Observatory Project Scientist and as Director of the Astrophysics Science Division. Dr. Clampin is a co-investigator with the Transiting Exoplanet Survey Satellite, TESS, and the Advanced Camera for Surveys Science team. His research interests focus on the study and the formation and evolution of planetary systems. Dr. Clampin graduated from the University of London with a BS in physics and from the University of St. Andrews in Scotland with a PhD in astronomy. Dr. Stephen Finkelstein is an associate professor at the University of Texas at Austin. His research focuses on the formation and evolution of galaxies in the early universe and the interplay of these sources with reionization. He makes use of the largest ground and space-based observatories and is the principal investigator for JWST Early Release Science Observing Program, the Cosmic Evolution Early Release Science Survey. Dr. Finkelstein received his BS degree from the University of Washington in astronomy and physics, and his PhD in physics from Arizona State University. And finally, Dr. Natalie Batalha is a professor of astronomy and astrophysics and the director of the Astrobiology at the University of California, Santa Cruz. Dr. Batalha's research focuses on exoplanet science, including both detection and characterization. She's the principal investigator for the Transiting Exoplanet Community Early Release Science Program with JWST to collect spectra of the atmospheres of a diverse set of exoplanets. Dr. Batalha was previously at NASA Ames and served as the project scientist for the Kepler mission. She earned her bachelor's degree in physics and astronomy from the University of California, Berkeley, and her PhD in astronomy for the University of California, Santa Cruz. As our witnesses should know, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. And when you've all completed your spoken testimony, we'll begin with questions. Each member will have 5 minutes to question the panel. So we will begin with Dr. Mark Clampin.
Chairman Beyer, Ranking Member Babin, and members of the committee, good morning. My name is Mark Clampin, and I'm the Director of the Astrophysics Division and NASA Science Mission Directorate. This is a great day for NASA, as you've all mentioned. As one of the many people who worked on the James Webb Space Telescope, I'm thrilled to join you this morning to share the groundbreaking science NASA and our partners, the European Space Agency and the Canadian Space Agency, are beginning to explore. NASA's JWST team was excited to join with audiences across the nation and indeed across the world for its launch, and then in July for the first science image rollout events. JWST was designed to discover the first galaxies and stars that formed in the universe, providing a view of the most distant light that we can see. Its discoveries will unravel how galaxies form and evolve. It will allow us to peer into stellar nurseries and study the life cycle of stars and the planetary systems that form around stars. And it will set us on the path to searching for evidence of habitable planets outside our solar system by providing a first look at the atmospheres of small rocky planets outside our solar system. JWST is already setting a rapid pace with new discoveries previously beyond our reach. In its very first full-color image, the galaxy cluster SMACS 723, NASA's scientists are amazed to see the deepest and sharpest infrared images of the universe ever taken. The combined mass of the foreground cluster of galaxies, which acts to gravitationally bend and magnify light from even more distant background galaxies, allowed us to see some when the universe was much less than 1 billion years old. So today I'm pleased to reveal the once hidden features of a protostar within the dark cloud L1527, which you'll see on the monitor, as it's just been imaged by JWST. Protostars are very young stars that are forming inside their parent molecular clouds. And this first image of this protostar with JWST shows that while the protostar itself is hidden, the view within the neck of this hourglass shape, you see a protoplanetary disk as a dark line across the middle of the neck. And to the top and the bottom, you see light from the protostar illuminating the cavities within the surrounding outflows of gas and dust from this object. JWST's unmatched sensitivity is also revealing new hints about the worlds outside our solar system. JWST confirmed the first clear evidence of carbon dioxide in the atmosphere of the gas giant planet called WASP-39b. This planet's discovery in 2011 was based on ground-based detections of the subtle periodic dimming of light from its host star as the planet transits in front of the star, essentially a mini eclipse. And JWST has now studied WASP-39 and discovered this carbon dioxide feature. So we expect that JWST will play a key role in starting the search for potentially habitable planets outside our solar system during the decade. Mr. Chairman, I'm always asked what is next and how do we build on the national investment made in JWST and its success. So firstly, we will be making lots of new discoveries with the unprecedented capabilities of the James Webb Space Telescope. In the near future, NASA plans to launch the Roman Space Telescope, which will conduct wide-field surveys to help us understand the nature of dark energy, the mysterious force which is causing the universe to accelerate as it expands. And a key recommendation in the National Academies for Science Decadal Survey in Astrophysics, known as Astro 2020, is the call for NASA to develop a new large space telescope able to survey and image habitable worlds around sun-like stars and then examine their atmospheres for evidence of life, what I will call a habitable worlds observatory. JWST, like Hubble before it, establishes US leadership in space science, and a habitable worlds observatory will continue US leadership in space science and scientific discovery by building on the breakthroughs in technology and science of the James Webb Space Telescope. It's truly an exciting time in astrophysics. Every day, one of my colleagues shares a new JW image or scientific result that is astonishing. Seeing JWST's first science images displayed in Times Square really showed that JWST science has captured the American public's imagination. So I would like to just conclude by acknowledging the contribution to this program by NASA's Nobel Prize winner, Dr. John Mather, who was an inspirational leader for the life of this program for the James Webb Space Telescope. Mr. Chairman, I'd be happy to respond to any questions you or other members of the committee may have.
Dr. Clampin, thank you very much. Wonderful overview. We appreciate it. Dr. Finkelstein, the floor is yours.
Thank you. Good morning, Mr. Chairman and members of the subcommittee. My name is Stephen Finkelstein. I'm a professor of astronomy at the University of Texas at Austin. I'm also the principal investigator of one of JWST's early release science programs. It's my great pleasure to be here today to share with you the early discoveries from our program, which is called the Cosmic Evolution Early Release Science Survey, or CEERS. CEERS targets galaxies forming in the early universe using several of JWST's instruments. I would like to take a moment to explain how the study of the early universe is even possible. This is thanks to two helpful features of nature, the first of which is our cosmic speed limit, the speed of light. When we look at distant objects, the light we see has traveled large distances to reach our telescopes. So we see these objects as they were in the past. While this is inconsequential in the nearby universe, when we look at distant galaxies, this allows us to see them as they were billions of years ago. The second way the universe helps us is that it is expanding. All galaxies are moving away from one another, and as light from galaxies travels through expanding space, the light waves stretch out. This makes galaxies appear redder than they should be, with the amount of reddening proportional to the distance. Astronomers assign this redshift a single number, which can be thought of as a time indicator. The most distant galaxies that the iconic Hubble Space Telescope can see are at a redshift number of about 10, where we are seeing them as they were over 13 billion years into the past. The universe is only 13.8 billion years old, so this is quite a feat from Hubble. However, Hubble is not capable of reaching greater distances. At redshifts greater than 10, light from these more distant galaxies is stretched so far to the red that Hubble, which is optimized for visible light, cannot see them. This means that the earliest phases of the universe, when the first galaxies form and evolve, have remained elusive. When did the first galaxies form out of the cosmic dark ages? What did they look like? Are their stars similar to those in our own Milky Way, or fundamentally different in some way? Enter JWST. With its larger mirror and sensitivity to infrared light, JWST was designed to target this early cosmic era, and that is exactly what we are doing with CEERS. We were fortunate enough to receive a portion of our data in mid-July, and I'm excited to share with you this beautiful image of the CEERS field. This image you see now shows a region of the sky about 8 times larger in area than Webb's first deep field, containing over 40,000 galaxies. The images at the bottom show a gallery of galaxies highlighting the exquisite level of detail achievable with JWST. As we analyzed these data in late July, one galaxy jumped out at us in particular. We continued to improve the quality of our images, and we became convinced that we were seeing a galaxy with a redshift number of 12, more distant than anything humanity had seen before. Here in this image, I present to you Maisie's galaxy. Maisie's galaxy, which is named after my daughter, as we both discovered it on her 9th birthday, and she had been asking me for months to name a galaxy after her, is shown in the zoomed-in panel, the small red dot. Here you are seeing light which has been traveling to us from a time only 370 million years after the Big Bang, looking back over 97% of the history of the universe. In a paper just submitted last week, we can now confirm that Maisie is not alone. Here I show you a compilation of 26 extremely distant galaxies discovered in our SEERS data, including an amazing galaxy at the top left, which appears to be at a redshift number of 16, which means that it's coming to us from a time only 250 million years after the Big Bang. This high abundance of early galaxies is surprising and indicates that something is fundamentally different about stars in these galaxies. While our sun is a pretty typical star in our own Milky Way galaxy, it has been theorized that early galaxies, due to their very small amount of heavy atomic elements, would have much greater typical star masses. These massive stars would lead to galaxies being more blue intrinsically and more luminous, allowing more galaxies to be seen in our images. And you can see that many of these galaxies appear blue in this image, indicating that we may be entering an epoch when galaxies are dominated by completely different types of stars than today. Given the unexpected nature of these galaxies, confirmation of their extreme distances is a must. This can be accomplished with spectroscopy, which is a type of observation where we take the light from an object and split it apart with a dispersive element like a prism to split the light into its component wavelengths, revealing significantly more information. JWST is scheduled to take a spectrum of many of these sources in the SEERS field just next month. These data will provide the needed confirmation of these redshifts. I would like to leave you with one of my favorite images, the Stevens Quintet early release observation. While this image features several nearby galaxies, if you look close enough, you can see plenty of galaxies in the background. JWST is so powerful that every field is a deep field. It is amazing to me that just 4 months ago, we had no idea that our universe started forming stars and galaxies so early. We are living in a transformative time in astrophysics, and JWST is truly revolutionizing our view of the universe. I thank you for your time and would be pleased to answer any questions.
Thank you, Dr. Finkelstein. So already they're finding galaxies older than your daughter. It's just, that's amazing. It's very cool, though. I hope you have other children. Okay, good. So, Dr. Batalha, the floor is yours.
Thank you. Good morning, Chairman Beyer, Ranking Member Babin, and members of the subcommittee. It is such a joy to be here to share the wonder of scientific discovery and the success of this new space telescope. Webb is performing at or even better than our expectations and has already achieved groundbreaking discoveries in our field. This is truly the beginning of a new era of exoplanet exploration, the hallmark of which will be the study of exoplanet atmospheres enabled by JWST. To date, over 5,000 planets orbiting other stars in the galaxy have been identified. Most were discovered using the transit method, which involves the precise monitoring of brightnesses of stars to search for the dimming of light that occurs if a planet eclipses or transits in front of its star. The bottom panel here shows how the brightness changes with time. This is the method employed by NASA space missions like Kepler and TESS. Those missions taught us that planets are common in the galaxy. On average, every sun-like star has at least one planet, and we estimate that more than 10 billion are potentially habitable in our galaxy alone. But these missions also taught us that the diversity of planets in the galaxy far exceeds the diversity of planets in our solar system. We need to better understand the physical processes that give rise to that diversity and their impact on planetary habitability if we are to find evidence of living worlds in the future. And that's where JWST enters the scene. Like Kepler and TESS, JWST observes transits. But Kepler and TESS observe them in white light, colors scrambled together. JWST can measure the dimming of light in hundreds of infrared colors simultaneously. Well, why do we care? Well, when exoplanets eclipse their host star, some of the starlight passes through the atmosphere on its way to our telescope. And the atmosphere imprints a chemical fingerprint on the light because each atomic and molecular species absorbs a unique pattern of colors. The net effect is that the planet blocks more or less light in each color depending on which molecules are present. These, in the next slide, are measured transits from a planet named WASP 39b, observed as part of our early release science program and shown here, stacked vertically in 25 different infrared colors. The host star is similar to our sun. Its transiting exoplanet is a little bit larger than Jupiter, but about the mass of Saturn, and it orbits its star 8 times closer than Mercury is to our sun. Now, these transits may all look the same, but there are subtle differences that JWST can measure. We can calculate the amount of starlight blocked by the planet in each observed color, and we plot that versus wavelength, as shown by the white points in the next graphic. This is the graphical representation of a planetary spectrum, the amount of light blocked on the y-axis versus wavelength or color on the x-axis. And it might not have the aesthetic appeal as Maisie's Galaxy or the Stephan's Quintet, but I would argue that it is just as profound regarding the mysteries it reveals. From this spectrum, we see a panoply of atomic and molecular species that we could not see before. The tallest bump or hill in this spectrum is due to the absorption of carbon dioxide molecules. We also see evidence of sodium, potassium, water, carbon monoxide, sulfur dioxide. The spectrum tells us so much more. It tells us there are patchy clouds. We learn that the atmosphere is enriched by heavy elements, suggesting that the planet was bombarded by planetesimals early in its life. And we even see evidence of photochemistry. The presence of sulfur dioxide cannot be explained without invoking starlight as a catalyst for the chemical reactions. High-energy photons from the star rain down on top of the atmosphere and break apart water molecules, triggering a cascade of chemical reactions leading to the production of sulfur dioxide. Photochemistry is fundamental for life on Earth to thrive. This is the first evidence of photochemistry, of a molecule that requires photochemistry for its existence. Over 70 transiting exoplanets will be observed by JWST just in cycle 1, hundreds over its lifetime. We now have a new lens on exoplanet diversity. From these data, we will gain insights into planet formation and evolution processes, and we will lay the groundwork for identifying habitable environments and living worlds in the future. Thank you so much for your attention, and I'm happy to answer any questions that you might have.
Thank you, Dr. Batalha, and thank all of you for fascinating testimony. And Dr. Clampin, I believe one of the images you showed us was the first time the public's seen that?
Yeah.
That's correct, yes. It was unveiled this morning. So
Great. Well, thank you for sharing that.
got to see it first.
Great. By the way, if there are members who wish to submit additional opening statements, your statements will be added to the record at this point. Well, let me begin our first round of questioning. Dr. Batalha, you talked about the photochemistry being necessary for life on Earth. And so we've made the leap of faith that photochemistry is necessary for life in general. Can we really say that? Is it not possible to imagine non-water-based life on other planets?
We only have one example of life, so we're going on what we know. But the rise of complexity in the universe takes a certain form. I mean, the very elements that are required for life are the very elements that the universe creates in most abundance. It's also the case that life harnesses energy to do work, to maintain itself, to evolve, to grow. So it needs an energy source. So the way that the host star interacts with the planet is a synergy, it's a symbiosis that is probably very common to the rise of complexity and to the rise of life. Could it be, is it certain that that's the only pathway for creating life? No. But it is true that whatever pathway that is, it's going to require energy, it's going to harness energy to do work, to maintain itself. That's a fundamental law of physics that we can't escape.
Great. Thank you very much. That's the best explanation yet that I've heard. Dr. Finkelstein, those stars you showed us that are so old, bright, and don't have the dense materials, is it safe to assume they're long since dead?
Yes, absolutely, that's correct. The most massive stars burn through their fuel so quickly, they live only a few million years at most. So we sort of caught them at a glimpse in time when they were shining very brightly.
On the whole issue of inflation, matter, antimatter coming into being, this rapid expansion, are we understanding that? And are there any insights on inflation that have come from JWST so far?
Not yet at this point. Inflation is happening at a very, very, very early epoch, essentially the instant right after the Big Bang. One of the things we can learn from studying the galaxies that come a while later, a few 100 million years later, is whether the abundance of galaxies, the masses of galaxies are consistent with our idea of what we call cold dark matter cosmology. So is there anything that we have seen yet to break that idea? And so far, it seems like you can explain what we see with ideas that we've had in the past. You don't need to actually fundamentally change cosmology, but again, we've only had a few months with these data, and a small amount of data has come in, so I would say stay tuned.
Great, very cool, thank you. Dr. Clampin, what is reionization, and why is that important? Microphone, Dr. Clampin, please.
Sorry. So reionization is when the first stars started to form in the universe and essentially ionize the intergalactic medium, or the medium that was present at that time. So it's a very important stage because it's the epoch when the first stars and galaxies started to form and change the nature of the universe.
Cool, very good. Dr. Finkelstein, you mentioned dark matter. I know it's been in a lot of the popular science recently that maybe that dark matter has been hiding inside the many more black holes that are out there than we thought. Is there anything that we're seeing in JWST that would give credence to that thought?
Not so far, but one of the most exciting things to come with the spectroscopy that we'll be obtaining in the next months to several years is it will give us our first chance to look at the formation of the earliest black holes in the universe. We know that today all galaxies have supermassive black holes at their center, but it's really challenging to grow black holes that large. And so we think, see evidence of them growing in these very early galaxies. And that's hard to see in the images alone, but you can see it with the spectroscopy.
Dr. Batalha, you're an astrobiology expert. I've heard tell that if you ask a room full of scientists how many believe that there's other life in the universe, every hand will go up. Is this something that you have to, is that the leap of faith you make before you commit yourself to astrobiology?
I think that's true. I myself believe that life has to be out there because complexity arises in the universe. It should arise everywhere. I think the fundamental question is how frequent is life, and is intelligent life common? That's a very different question. If I had to posit a guess, which scientists don't like to do because we like to have evidence, but if I had to posit a guess, I would guess that living worlds are common. And by that I mean microbial life. Whether or not it evolves into intelligent life is another question. And I'm not so sure if intelligent life is going to be common or rare. But we know how to find out.
Thank you very much. I appreciate all of it, and let me introduce the ranking member of the committee, Dr. Babin.
Thank you. Very, very, very fascinating information. Dr. Clampin, JWST was apparently hit by some micrometeorites after deployment. I also noticed this morning that NASA announced a new strategy to minimize future damage to the spacecraft. What impact did those strikes have? Can it be quantified at this point? What were the impacts greater than planned? Is JWST more susceptible than expected? And is there anything that can be done from an operational standpoint that can mitigate the risk of these micrometeorite impacts? And would those modified operations impact the planned science? I know, and I can repeat this, but if you could answer some of those, I'm very curious to hear, to see what you all had planned before and what you have planned in the future.
So to date, we've seen, I think, 14 micrometeoroid impacts, and the majority of them are what we call very low energy. We've seen one which has significantly higher energy, and I'll come back to that in a minute. But when we designed the telescope, we designed all the science requirements to what we call the end of life, assuming that in that environment there would be micrometeoroid strikes. And we have a very detailed model that's provided by the Marshall Space Flight Center for the environment at the second Lagrange point where the telescope's operating. So we knew that we were going to see micrometeoroid strikes, and we built that expectation into the performance for the end of life so that we would get to the end of 5 years, which is the nominal lifetime, with an operational telescope that was still producing the science requirements. As I said, we've seen 14. One of them was a little bit of a surprise in that it seemed to have, it was higher energy than expected based on the model. And we think that that may have actually hit a piece of the mirror which produced a more significant effect than the rest of them. That said, because the telescope is comprised of 18 individual segments, with each of them having 6 degrees of freedom and an additional degree that allows us to change focus, we've been able to compensate for the impact that that particular micrometeoroid had. And so we are still returning image quality that's much better than we originally expected from the requirements. In order to make sure that we're playing it as safe as possible, we are looking at operational changes for the second cycle science, where we avoid pointing the telescope in the direction where micrometeoroids would have a sort of direct normal impact on the mirror. And this is really just going to affect when in the year People Science gets done. So you can look at objects, twice a year, and it just depends on how you schedule the science. So we're not expecting any major scientific impacts. And for very special targets that we may need to point into the RAM, we will, provide a waiver to do that. So I think the answer to your question is we expected this, and we're being very conservative and making some operational changes to make sure that we minimize any future impacts.
Okay, thank you very much. And a question for all. JWST is arguably the most powerful and advanced space telescope in operation. China, however, is planning to launch a space telescope next year that will co-orbit with their space station in low Earth orbit. How does this telescope compare to Hubble, JWST, Roman, or other great observatories? And what are the advantages and disadvantages of a co-orbiting observatory in low Earth orbit?
I can take that one. So I don't know a lot about that particular telescope, but I can say a couple of things. First of all, you always worry about the contamination environment around a space station, which can result in residue or volatiles getting onto the primary mirror. That it potentially impacts your ability to do science in the far ultraviolet. That said, otherwise, I think potentially the performance is likely to be similar to that of Hubble in the visible, imaging bands.
Okay.
Given that it's in low Earth orbit.
Dr. Finkelstein or Dr. Batalha?
Congressman Babin, I don't really know a lot about the platform, so I can't offer in detailed comments about the comparison. Sorry.
All right, thank you.
Yeah, same for me.
Okay. Thank you, and I'll just yield back. Time's up.
Thank you, Dr. Babin. We now recognize the gentleman from New Jersey, Mr. Norcross.
Thank you, Chairman, and I'd like to thank the witnesses for being here and keeping my curiosity of the world alive. It's why I enjoy so much this subcommittee. So, not to be a buzzkill on this, but the issue comes to the mechanics. We're seeing where and the potential where we're going. Are all the systems, Dr. Champion, up and operating as expected today?
Yes, JW is operating exactly as we expected it to operate, and as we've said, it's exceeding many of the science requirements that we built it to.
Are there items that are on schedule to be looked at further or newer in the operational life of this that you want to get done now that because of what might happen will not be as effective in 5 years?
No, I think we're going to take the approach of, as we have done with Hubble in the past, having a competition every year called the proposal cycle, and a peer review panel will select the very best ideas, and we will basically do those programs with the telescope, making sure that we get the best possible ideas each year done and those science programs completed.
Okay, so being first, other than to answer those questions, is not a mechanical issue of something that will be done. Great.
No.
So, what are the potential issues, or as I say, what keeps you up at night on this telescope?
So we built this telescope and tested it extensively on the ground. And I'll be honest, most of the issues that kept me up at night were the initial deployments and the whole process of commissioning the telescope and getting it to the point it is today. Right now, I'm very comfortable with the way the telescope's operating, and I think, as you've seen from the science results that have been presented, that we're really very happy with the way it's operating. You also may be aware that the initial launch was extremely precise and put us into an orbit that allowed us to minimize the expenditure of propellant. So we are anticipating something like a 20-year lifetime based on what we call the consumables, which is the propellant that are needed to, first of all, keep it in its orbit at L2, and secondly, just to do what we call desaturate the momentum wheels every few days. So right now, we're very comfortable with the way the telescope's operating.
Would you be comfortable saying that you have exceeded all the expected outcomes that this telescope is going to do?
I would certainly be comfortable, and I'll give you one example. I mean, our image quality, which is defined in terms of what's called a wavefront error, was when we got the commissioning done, we were basically at half the wavefront error that we expected to be at. And what that means is sharper images, better sensitivity, and you combine that with the pointing, which came in at 1 milliardsecond versus the requirement of 7, and you have a telescope that's more sensitive with sharper images than we had anticipated.
One of the core obligations we have is oversight, and we quite often hear in government how things don't work. I just want to say thank you for exceeding our expectations, and let's continue, and with that, I yield back.
Thank you, Mr. Norcross, very much. Now I'd like to introduce the congressman who last night had the most important congressional district in the country, Mr. Posey.
Thank you, Chairman Beyer, for holding yet another exciting committee meeting, and thank you to the panelists for your fascinating testimony. This has got to be the most enjoyable committee in Congress. Dr. Clampin, I represent, as Chairman said, the Space Coast at Kennedy Space Center. So James Webb was launched last year from Cruz in French Guiana aboard an Ariane 5 launch vehicle. And fantastic launch. I applaud the accomplishment. But just, I'm wondering, going forward, are we going to launch any future observations on foreign soil, or are we going to use U.S. soil?
So let me start by just congratulating you on a great launch from the Kennedy Space Center last night. It's really thrilling to see Artemis finally get off the ground and roaring into life. In answer to your question, we live in a very different world now where there are lots of different U.S. commercial launch opportunities, including a number which provide us with new capabilities that we're definitely thinking of as we look at the Astro 2020 Decadal Survey. But just to give you a couple of examples, the Roman Space Telescope will launch on a Falcon Heavy, and many of our SMD missions are now launching on U.S. launchers. So my expectation is we will take advantage of the new U.S. launch capabilities that have been provided to us.
Thank you very much. Dr. Batalha, hope I didn't mess it up too badly. Can you walk us through the process of gaining observation time for James Webb? You know, how it's organized. Is it any different than other observatories, or do you have any thoughts on how it's working so far?
Yes, absolutely. It follows the same model that was used by the Hubble Space Telescope and actually many ground-based observatories as well. It's highly competitive, as you can imagine. The scientific community writes proposals, submits them. There are experts who agree to serve on a committee to review those proposals. It's a blind review, so you don't see the person who's leading that team. You don't see their name. That's meant to mitigate biases that the review committee might have. I've served on both the Telescope Allocation Committee and on the executive committee of that process, and I can say that it's very thoughtful with regards to technical feasibility and the impact of the science and balancing the portfolio of the telescope.
All of you commented on this, if you would, how the James Webb will contribute to our understanding of the supermassive black holes compared to what we learned from Hubble.
Absolutely. So as I mentioned, we have reason to believe that these black holes are forming and growing in the early universe. And black holes can be tricky to see. They don't emit light themselves. So you have to find black holes that are either interacting gravitationally, so you can see motions, which is also very difficult, or that are actively accreting gas. And as that gas spirals into the black hole, and the black hole gobbles it up and grows in mass, it gets quite hot, and that light can't escape. And that process is very energetic, and so there are unique signatures that you could see in a spectrum. And so this is, I think, one of the most exciting things I'm looking forward to in the next month is some of those are going to be very obvious signatures, and we'll know right away, yes or no, there are black holes growing in these galaxies. If we don't see those signatures, that might be even more exciting because you still have to make these big black holes by today. Yeah. And if our best idea is that they kind of slowly grow throughout the universe is sort of disproven, then there are more exotic scenarios, such as maybe the early universe makes modest-sized black holes in what we would call a direct collapse black hole scenario. You could make a black hole out of a pocket of gas that's 1,000,000 times the mass of the sun, so you're already kind of making baby supermassive black holes early on. And maybe if that's the case, maybe there are ideas about how we might be able to see those in some of the deepest imaging that's upcoming with JWST. And so no answers yet, but I think in the very near future we'll have either good answers or good additional questions.
Thank you. You mentioned the universe being 13.9 billion years old. What was before that?
My favorite answer to that is your guess is as good as mine. A more technical answer, which I don't like, is that the concept of time only exists as long as the universe exists, so there was no before. We can measure very precisely the evolution of the universe as long as the universe has been around. We can measure very precisely the age of 13.82 billion years. Why the universe began, what came before, if there is even a concept as before, that we don't know. And it's very hard to test because to do science, we need to make observations to test our theories. And we only have the universe that we live in right now.
And beyond the universe?
The universe is infinite as best we can tell. And so there is no beyond the universe.
Thank you, Mr. Chairman. I yield back.
Thank you, Mr. Posey, very much. Now let me recognize Congress's greatest champion for travel to Mars,
So much fun.
the gentleman from Colorado, Mr. Perlmutter.
Thanks, Mr. Chair, and I want to thank the panel and all your colleagues for your persistence and your perseverance with this project, because it had a few ups and downs over the course of its life, and I want to thank this committee for its patience, because the scientific products that have come from this are just remarkable. So, Dr. Batalha, I want to start with you. How do you choose what exoplanets you're going to study? I mean, you said there's a whole bunch of them, but you picked 70. And then I'm going to talk to you, Dr. Finkelstein. How do you choose what galaxies you want to look at?
Great question. There are over 5,000 exoplanets that we know of, but not all of them are bright enough for us to study their atmospheres, even with Webb. So there is a NASA mission called TESS, which is doing an all-sky survey to find transiting exoplanets that are near the solar system. Those are the ones for which we can get really good precision, part per million precision, to see these bumps and wiggles in the spectrum that are telling us about the presence of molecules. So the list gets whittled down. There are still hundreds, even after that, many hundreds. And so you look at this kind of science questions that you want to answer. There is an exoplanet, or a star called TRAPPIST-1 that is very close to us, that harbors 7 exoplanets orbiting it, 3 of which are in the habitable zone, orbit in the habitable zone. So you can imagine that we are spending a good deal of time observing those planets. That's going to be a high priority target.
So how do you and your colleagues choose who's going to study what planet? How do you share information
Yeah.
among all of this? I mean, how is it open? Is it closed? Is it, you know, I got planet X, you got planet Y, we don't talk to each other?
Yeah, it's a little of both. For the early release science program back in 2016, I started an open committee. It was open to everybody who wanted to participate. We have over 300 scientists who participated in that process in order to create a truly grassroots strategic plan for what the very first exoplanets we would observe should be. So that was an open process. The data is non-proprietary. Anybody who wants to participate can. It's truly open science, and that's been a very valuable exercise for how we do science.
Great. Dr. Finkelstein.
Yeah, thank you. So first, I also want to acknowledge the large number of people that made this possible, including the Sears team. Not quite 300. We have about 200 scientists in our team, and of course the engineers that made this telescope possible, and the people doing the work, which is usually the junior scientists, the graduate students and postdocs. So how did we decide what galaxies to see? Well, we didn't know these galaxies. We were discovering them. So we are doing what we call blank field astronomy, which was a wild idea first tested out in the mid-1990s with the Hubble Deep Field. The Hubble Deep Field was kind of a bold idea to point at what we thought was an empty place in the sky, spend a couple hundred hours observing, and see what you find. And I think many people thought you would find nothing, and it turns out you see the universe is filled with galaxies. And that's become a very useful strategy now. We know that there are galaxies pretty much no matter where you look. So then the next question is, why did we look at this particular place in the sky known as the extended growth strip? And the reason why is that Hubble had looked there before. And the Hubble data is very, very useful for the JWST data. Hubble has the visible wavelength data that's just crucial to combine with our infrared data. And finally, one key part of our early release science program in particular is we're using multiple instruments with JWST, and we want them all to overlap the same place on the sky. And it turns out with a sort of fate of geometry, this extended growth strip field is kind of a strip in the sky, and JWST can look at that strip at just the right angle to allow the instruments to overlap. So it's a nice combination of things that allow us to point here.
Thank you. And Dr. Champlin, last question. As you built the telescope, and, you know, there were a few hiccups along the way, what would you do differently today if you were going to build another telescope like this?
So I can spend hours talking about this, but I helped chair a NASA study called the Large Mission Study, and I was the person who put together the plans for how we would formulate the next mission differently. So the first and most important one, I think, is you need to focus on schedule from the beginning. You also need to get the technologies to fully matured before you start actually designing the mission. And I don't just mean 6 or 7 individual miracles. You have to remember that those miracles have to work together. So the biggest challenge on these very large missions is the system, not the individual technologies. So think about that and make sure you don't overdo the science requirements and you keep focus on the key science that you want to do. And I think that's the path to success.
All right, thank you. I yield back to the chair. Thank you.
Thank you, Mr. Perlmutter, very much. And we recognize the gentlelady from California, Ms. Kim.
Thank you, Chairman. And I want to thank all of our witnesses for joining us today. I also want to echo my colleagues in congratulating NASA for the launch of Artemis 1, how exciting it was. I was there the first time when we thought we were launching, and 4th time is a great charm. This launch truly marks the new era of space exploration for the United States and its international partners, and I'm looking forward to the future Artemis and NASA eventually landing astronauts on the moon. The James Webb Space Telescope was years in the making, as we all know, and it's really exciting to see, how despite all the, challenges that we faced in the development, we saw last Christmas a wonderful gift that, as we watched the James Webb Space Telescope finally launching ESA's Ariane 5 rocket. And early this year, the world watched as NASA released James Webb's first fully developed image of cosmic cliffs in the Carina Nebula. So exciting. So I want to congratulate NASA, ESA, and CISA. And there are many partners for the success of your mission. And while there are many lessons still to be learned from telescopes development, I'm pleased that we're taking this opportunity to examine and celebrate the scientific achievements of the James Webb Space Telescope and to hear more about the telescope's future observations. And I want to start with Dr. Clampin. I want you to know that much of my key focus on this committee is STEM engagement. So can you speak to the STEM engagement opportunities that this JWST has provided NASA with? And can you specifically talk about NASA's K through 12 engagement?
So we have had a very active and vigorous STEM program from the very beginning of JWST. And you can see from the engagement of the public, there's this iconic image of somebody standing in Times Square taking a picture of a JWST image as it comes up on the display. So we are heavily invested in every stage of STEM education. And the great thing about astronomy and astrophysics is it's a very accessible science for all ages. And so it's really good for bringing in young people into STEM careers and getting them engaged. We also at NASA have a very vigorous, education support program, and I'd be happy to get you more information on that.
Great.
Yeah.
While much of the mission of JWST is to examine what is beyond our solar system, we were amazed by the clearest image of Jupiter that we've ever taken. So can you describe JWST's observation of Jupiter, what it has taught us, and about our own solar system? Yes.
So for me, the observation of Jupiter was amazing because we spent a large amount of time trying to figure out how we would observe something as bright as Jupiter without completely saturating all the sensors. In fact, point of fact, it turned out that our calculations had really been spot on, and we were able to take images of Jupiter. So most of the science that JWST will do in this field is more in the form of long-term monitoring, with understanding what's going on in the atmosphere of Jupiter and tracking it over time. So the first image is just the first step in a long program of tracking what's going on with the atmosphere of Jupiter. The other part that's also very interesting, and there are a number of programs approaching this, to study the moons of Jupiter and also the other gas giant, Saturn. And it's the infrared opportunities and the ability to do infrared spectroscopy of their atmospheres that present really interesting opportunities. And those observations are still to come.
Valuable lessons and observations. Thank you so much. Looks like I'm running out of time, so I'll yield back.
Great, thank you
Thank
very much. Let me recognize the gentleman from Florida, Mr. Webster, for his questions.
Yes, I got here a little late, but and maybe it's been asked, but how do you determine with the vast amount of space and how do you determine the initial direction that you're going to point the telescope and take a picture, and how deep do you go? How do you determine that? Anybody?
Yeah, so for distant galaxies, it sort of really doesn't matter where we point. There's a variety of factors. You want a place that has the longest observability window. As Dr. Clampin said, you can't look everywhere at all times. Sometimes the sun is in the way, things like that. And you want places that are sort of pointing out of the plane of the solar system and out of the plane of the galaxy, because you don't want a lot of dust that's in our solar system in the way, called zodiacal light. And you don't want light from stars. We don't, for our galaxy surveys. And then for how long you observe, that's always critical when we write these proposals that Dr. Batalha was talking about. It's crucial to have a very good estimate of how much time. You can't just sort of say, oh, we think we need 10 or 20 hours. You need to say, we know. And so NASA has developed tools to estimate the sensitivity before launch of the telescope. And we have some idea of the faintness of the galaxies we want to see. And this calculation tells us, here's how long we think you should observe. And then we take it one step further now. NASA has also helped develop excellent data simulation tools. And so you can say, okay, let's say this exposure time tool said you need 2 hours. Let's actually simulate the data. Do we actually see the galaxies in those 2 hours? And we did that process for our early release science proposal to show that, yes, we can actually do it. And then it turns out that the telescope was working even better than expected. So we can see a little bit fainter than we thought we were going to.
So you have a, is it mapped out already and where you're headed and what you're doing and where you're staying and how long you're going to look and all of that? Is that something that's mapped out ahead of time?
So it's a year-by-year process, and so the telescope is currently executing its Cycle 1 observations, and proposals for the next year, called Cycle 2, are going to be due at the end of January, and so sort of a year-by-year process.
Well, that's very, very interesting. So once you, but how far ahead are you? I mean, what are you looking at? Are you just a year ahead in that you've done 1 year, you've done another year, and you won't do it the next year until you finish the second year?
Yeah, we're sort of close to the midway point of that first year of observations, not quite there. And so there is some amount of multi-year planning. Eventually, the Hubble Space Telescope got to a mode where they did accept multi-year proposals, and JWST may eventually get to that point. But right now, there is so much exciting science to do. We want to try and get as many, observations in, covering as many targets as possible, and then we can start to think, here are some maybe longer-term ideas that you might want to do.
So if you find something that's interesting, do you still just move on or do you stay?
Usually you have to propose for the next year. I will say, I mentioned we're getting spectroscopy next month. Part of that is a particular type of observation called a director's discretionary time proposal, where if you find something exciting, you can kind of appeal to the director of the Space Telescope Science Institute. And they have an amount of time they can give out for, I like to call it emergency time, really exciting observations. Often it's exploding objects like supernovae that are fading. You really need to get to them. In this case, it's a really exciting distant galaxy. We'd like to know if it truly is the distance we think it is.
Awesome. I have other questions, but I don't know what they are. Thank you so much.
Thank you, Mr. Webb. So we will do a second round if it occurs to you after Ms. Bonamici. Ms. Bonamici, you are recognized.
Thank you, Chair Beyer and Ranking Member Babin, and thank you to our witnesses for your expertise and your testimony. I'll join my colleagues in congratulating NASA on the successful Artemis launch. This has been a very exciting and certainly thought-provoking hearing this morning. We know that space exploration has played such a pivotal role in uniting our country and our world, but also in broadening our understanding of our place in the universe, inspiring future generations of scientists. And I think back to July when the first images came out. And I know you've mentioned a couple times the Times Square display and really how stellar those, I guess pun intended, photographs were and continue to be. And I want to, of course, acknowledge not only the federal investment, but the more than, I think, 300 universities and all the participation and partnerships that made this happen. I've discovered, certainly over the years on this committee, that we've had many discussions about how do we increase the appreciation among our constituents and people in the country and around the globe of the work, of the science. How do we get peak interest in further studies, and how do we make sure that our communication with the public gets across the importance of what's happening? And so I know Representative Kim asked about education. I wanted to first ask our professors, Dr. Finkelstein and Dr. Batalha. You're both professors. What have been your experiences since the successful photographs started coming out in July? How has this changed among your students, among prospective students? Has it changed their views? And what program should we engage in to make sure that, invest in to make sure we're engaging students to further their careers in science?
Great question. The data, the images, the scientific discovery is so inherently alluring. It's very easy to talk about it with our youngsters. I've spoken to elementary school students, to Girl Scouts, and high school students, and people in community colleges, and the public, and everybody is just, eyes like saucers. I think that science, you need to communicate the wonder of it and how it maps to meaning, what it means to be a human. For me, I got a late start in science because I couldn't map the science to scientific discovery. It's hard to understand that feeling of scientific discovery and how absolutely joyful it is. Carl Sagan called it a kind of ecstasy when you have that deep understanding. So taking these images out into the public, I showed the deep field, and I told the public, when I look at that image, I marvel at how much life must be captured in all those galaxies, thousands of galaxies and billions of stars. So I think that's what we need to do. Of course, you also need the rigor of the classes, the coursework to go along with it, and mathematics, showing the joy and fun of mathematics and science curriculum is also extremely important.
I'm going to ask Dr. Finkelstein to go in a related direction. If we want to maximize, and I'll ask this to Dr. Champlin as well, if we want to maximize the scientific return from James Webb, what types of skill sets and educational background do we need? And right now, is the research community well positioned for working with all the data that's coming in?
Yeah, that's a great question. So I think space sells itself. It's really easy to get anyone interested in it because it's so amazing. For me, it's really about trying to chase our origins, the ultimate origins of where the Milky Way galaxy came from. We need students in the STEM sector, and space really inspires students to go that route. Some of those students choose to go into astrophysics, and that's fantastic, and then we get to work with them at universities. And something that has become more and more common over the last decade or so is more undergraduates participating in research. And so we have a number of undergraduates that are working with us on these data, and I know that's true around the country and around the world, and that gets them the real experience of what it's like to be an astronomer and to make discoveries and have those aha moments and really say, oh, this is something that I could actually do for a living.
That's great. And it looks like I'm just about out of time, but Dr. Champlin, if you have just a sentence, it would be helpful.
I would just say one of the things I find really inspirational is a lot of my students that when I was at the Goddard Space Flight Center were inspired to join NASA because of what we did with Hubble, and we will do the same with James Webb.
Terrific, thank you. And as I yield back, Mr. Chairman, because I can't stay for a second round, I just want to mention the importance of diversifying the workforce and making sure that the opportunity to work in this field is available, especially to those historically left behind. And I yield back. Thank you, Mr. Chairman.
Thank you, Ms. Bonamici, very much. Now ask unanimous consent on the committee to waive on Ms. Stansbury and without objection. Let me now recognize online Ms. Stansbury for her questions.
Thank you so much, Mr. Chairman, and thank you to the committee for letting me participate today. As folks have noted already on this hearing this morning, we're not only celebrating the findings of the Webb telescope, but also the successful launch of Artemis 1. And as a woman in STEM, I want to just note that it's being led by an amazing group of women, including Charlie Blackwell Thompson, who is the first woman ever in American history to oversee a NASA countdown and launch. And so this is long overdue in history making, along with all of the scientific discoveries that we're talking about this morning. And I too want to add to the chorus of everyone who's been working on the Webb telescope and the science that's coming out of it. After 3 decades of bipartisan work, dedicated collaboration by our extraordinary scientists and engineers at NASA, our space industries, and of course, scientists across the world, this amazing telescope launched last December. And I want to say on a personal note, I was among the millions of people who stayed up late through the night and into the morning on Christmas morning to watch the launch of this telescope, and had the extraordinary opportunity when I was working on space policy at OMB as a staffer to actually see the assembly of the telescope at Goddard. And so it's really been an exciting journey to see the telescope launch and everything that's coming out of it. In my home state of New Mexico, which is a powerhouse in science and technology and aerospace, we could not be more excited about the Webb telescope and what it's teaching us about the origins of the universe and our place in it, but also helping to inspire the next generation of scientists and researchers who are not only engaged in this work, but also the students who we've been talking about this morning, who are inspired by what we're finding from this project. In particular, Professor Tony Hull, who's a professor at the University of New Mexico, was part of the team that helped to polish the telescope's mirrors, which are bringing these extraordinary images back to us. And other scientists at our major flagship university, including Professor Dragomir, is working as part of a team to explore exoplanets and unique phenomena outside of our solar system. As we've been discussing this morning, the discoveries of this telescope not only will tell us more about the universe and our place in it, but are helping to excite and energize a whole new generation of aerospace engineers and scientists and thinkers about the universe. And so I want to use the remainder of my time to ask each of our three panelists two questions. The first is, what are you personally most excited about and surprised about what we're learning from the telescope? And the second is, what is the next chapter of exploration? What are we learning from the Webb project that is telling us where we need to extend the frontiers of science and knowledge? So starting with Dr. Clampin, maybe could you share your thoughts on what are you personally most excited and surprised about and what the next chapter is?
So I've been most excited by the transmission spectra from exoplanets that Dr. Batalha showed. I think they're really exciting, and I'm looking forward to seeing observations of the TRAPPIST-1 system come in. As far as where we go next, I think the next big challenge is the search for life, and I talked briefly in my initial remarks about how we will address the decadal survey, the National Academy's decadal survey, by trying to build a 6-meter or more space telescope that will look for habitable exoplanets around solar-type stars and then characterize them to look for evidence of life. So that's kind of where I think we're going next.
Thank you. And Dr. Finkelstein?
So I think for the near future, what I'm most excited about is to look even deeper. The early release science images I've shown you, they're very shallow. They're less than an hour of exposure time. And in cycle 1, there are a number of deeper programs, including a public deep field called NGDeep that will be observed at the beginning of February. And so soon we will have the JWST equivalent of the Hubble Ultra Deep Field. Into the future, in the not too distant future, I'm extremely excited about the potential of the Nancy Grace Roman Space Telescope. One of the exciting things we're finding is that the early universe has big, bright galaxies, and that telescope, although it has a smaller mirror than JWST, has a much larger camera. It's optimized for finding these massive, rare beasts in the early universe, and it's going to be fantastic to have that capability very soon.
Amazing. And Dr. Batalha?
Yeah, I will echo what Dr. Clampin said, but I wanted to add one thing about the exoplanets. The most common type of planet known to humanity right now is a kind of planet we don't even have in our own solar system. It's intermediate to the rocky terrestrials and the big gas giants. We call them super Earths or sub-Neptunes, but actually we don't really understand their nature. Is this more real estate for life? That's a big question on our mind. And this is a class of planets that JWST will be able to characterize and shed light on exactly their nature. I'm very excited to see that happen.
Amazing. Well, thank you all. And again, congratulations to NASA and to all of the teams who worked on this amazing project and for all of the exciting scientific discoveries yet to come. Thank you, Mr. Chairman. I yield back.
Congresswoman Stansbury, thank you very much. We'll now begin a second round of questions with Dr. Babin and I, at least, and me. Dr. Batalha, if you forgive me wandering a little bit, I think one of the most interesting questions in politics is, does history have a direction? And I know it's sort of a metaphysical question, but I was really intrigued by your comments about increasing complexity and the universe coming together to continue to form the elements. Back at the beginning, I guess there's only hydrogen, and now we have this incredible, and then combining that with Shannon's second law of information, that there is always more information in the universe in this instant than there was the instant before, along with the second law of thermodynamics, which talks about everything moving to the lowest energy state. How do you put that together? Can you put that together in a way that suggests that the universe has a direction, and that direction is complexity?
That's a very good question. We grapple with these questions. I think that they're fundamentally tied to how we see our place in the universe and how we find meaning. We observe this complexity arising. It seems very logical, like it's going to proceed the same way everywhere. The building blocks of life are in the galaxy. We see carbon dioxide, we see water molecules, we see this rise of complexity, even more complex molecules that reside in protoplanetary disks and in star formation clouds. So it seems very logical that life is just another step in that process. But you're asking a bigger question, which is what happens to life? What really is going to happen to us? Are we going to survive into the future? What does it look like if humans become spacefaring creatures? How does that affect our evolution, both cultural and biological? And those are questions that I can't answer. I don't even know if we will survive to the future or if that's a given. I don't know if the universe evolves towards goodness. These are all questions that I think are up to us. What I know is that we have the ability to affect that outcome, whether or not we survive to the future. And when we study planets and we understand the limits of habitability, we learn something about the sustainability of life right here on planet Earth. And that's one of the main motivators, I think, for studying exoplanets with JWST.
Thank you for answering a difficult question. And thanks, too, for pointing out that there's a difference between the question, is there life in the universe, versus the question, is there a consciousness, other consciousness in the universe? Yeah. Very, very different potential answers. Yeah. Dr. Finkelstein, you talked about, you showed the incredible picture of all those different galaxies across the bottom. They look like 6 or 7 different varieties right there. Can you talk about the structure of galaxies? I mean, we're used to thinking the Milky Way and the spiral galaxy, but it looks like there's more going on.
Yeah, absolutely. So there are a wide range of morphological differences in galaxies, and I have a bias. I think the spiral ones are the most beautiful, and one of the amazing things about some of those small panels is you can actually pick out the star clusters, those tiny little knots or pearls in those galaxies. Those are clusters of hundreds or thousands of stars just forming. And I didn't show you comparison, but if you look at the Hubble images of those galaxies, a lot of that detail is lost. And so one of the results I showed you in the written remarks that I didn't have time in my statement was what we are already learning about the morphologies of galaxies. And in fact, when we first made that big image, we actually put it on a huge 30-foot television screen we have at the Texas Advanced Computing Center. And one of the things we realized is when you look at the small galaxies, you see some spirals. And because they look really small, they must be really far away. And with the Hubble Space Telescope, at the limits of Hubble, we thought that once you get about 10 billion years or so into the past, you don't really see spiral galaxies anymore. Everything is kind of in a regular clump. But now with JWST, we have the resolution. It turns out the spirals were there. We just could not see them. And so you see them out to redshifts of 2 and 3. You see barred spirals, these elongated features in the center, similar to our own Milky Way galaxy. We found the highest redshift barred spiral at a redshift of greater than 2, so that's over 10 billion years into the past. And we see evidence that galaxies have these ordered disks, these ordered rotational motions, out to maybe even 1 billion years after the Big Bang. And if you ask some of the theoretical astrophysicists, they would say, we knew that was there, you just couldn't see it before, but you never know until you look. And now we finally have the observations to prove it.
That's very cool. You're making me jealous talking about the 30-foot TV. One more question. I think maybe to a question from Mr. Posey or one of my Republican friends, that what's beyond the universe. Typically, we're thinking that the definition of the universe was as far as light has expanded, rather than being infinite, that is still expanding into whatever's beyond it, or nothing that's beyond it.
Yeah, I just taught this earlier this week in my class. So that's the difference between the observable universe and the entire universe. So the universe has been around for a finite time, only 13.8 billion years. And so we can only see objects that were close enough that their light has been able to reach us in that period of time. But to our best understanding, that is not all there is. There is more universe out there that is inaccessible to us right now because the universe has not been around long enough for that light to travel to us.
Great. Thank you very much. Well, now we recognize Mr. Babin for his questions.
Absolutely fascinating. Thank you. I'm going to bring us back down to earth for congressional oversight here, okay? Dr. Clampin, the Government Accountability Office, the NASA Inspector General, the National Academies of Science, and this committee conducted a significant amount of oversight on the JWST program over the past 20 years. We've learned a lot about what to do and actually what not to do. As NASA continues with the development of the Roman telescope and begins to consider other follow-on observatories, what are the top 3 lessons learned from JWST that came out of all these reports, these audits, these investigations, and independent reviews? If you could, I know that's digging deep, but if you could tell us some of the fruits of our labors up here.
So I think a lot of it comes down to how you formulate these missions at the very beginning, the phasing of how the different pieces get put together. One of the things we did on JWST, for instance, and some other programs is basically get too far along with the spacecraft or the absolute mission design before we competed the instruments. So then we need to sort of make adjustments to accommodate the instruments. So the first thing for me is you make sure that all the technologies are at the required maturity level and that you understand how they're going to work in the architecture that you're formulating. So you really have to think about systems rather than individual boxes of technology. I also think the schedule is very important, and trying to formulate and execute a mission to the schedule from the very beginning. And that's something that I'm very focused on doing for the next response, as we respond to the National Academy, thinking about the next big large mission, which is this, what I call Habitable Worlds Observatory. Getting all the technologies mature and at the point where we understand how they work together as a system before we start formulating the design for the observatory. And then once we start building the observatory, we're really focused on building it to a schedule. So those are the 2 main things for me. The larger missions really require this systems level focus, and making sure you understand everything before you sort of launch into it is very important. I'm now, as I'm sure you're aware, responsible for making sure that Roman comes in on schedule, and Roman's already well along, and one of the things that I'm doing there right now is just making sure that we're addressing issues that have arisen as we've come out of the pandemic, workforce issues and supply chain issues, and we've been working to put in place with our industry partners innovative approaches to addressing some of these so that we stay on schedule.
Yes, sir. Thank you for your service, too. A second question for you, if you don't mind, Dr. Clampin. NASA paused JWST science observations using the MIRI medium resolution spectrometry mode on August the 24th because of increased friction in one of its grading wheels. NASA concluded the issue was likely caused by increased contact forces between subcomponents of the wheel's central bearing assembly under certain conditions. NASA announced that it had developed and successfully tested a plan on November the 2nd, and that it would resume MIRI MRS science observations on November the 12th, starting with a unique opportunity to observe Saturn's polar regions just before they become unobservable by Webb for the next 20 years. Was NASA successful in implementing this plan? And how is MIRI MRS mode functioning now? And what level of confidence do you place on the issue being resolved and that it will not be an issue in the future?
So let me just assure you that, yes, we did get the observations of Saturn done. So I actually got an email late yesterday saying that they've been completed. We have a plan of incremental steps to bring this particular mode of the instrument. It is a mode, it's not the whole instrument.
Yeah.
So we're bringing that back, step by step, exercising the wheel, checking all of the engineering telemetry, making sure we understand how it's performing as we return it to what I'll call normal service.
Okay, good. Thank you very much. And I'll yield back, Mr. Chairman.
Great, thank you. And I now recognize gentleman from Florida, Mr. Webster, if you have any additional questions.
I think I do.
Great.
We'll see.
Floor is yours, sir.
This is to anybody. There's one picture in here, Southern Ring Nebula. How wide, or what's the dimensions of that nebula?
I have to say, I think we'd have to get back to you on that. Off the top of my head, I do not recall.
So would you know the dimensions of any of these photos as far as millions of miles, billions of miles? Or maybe you don't even measure them in miles. I don't know.
I think most of them have that information in the comments that go with the plate. I mean, they're all so very different. One's, a planetary nebula in our galaxy, and others a very deep image of the sky. But we can get you that information.
Great. So have you, among yourselves or among just the people that work on this, do you take a poll and see what's the most fantastic display that's been, or people have their own ideas, or is there one that sticks out as just the most phenomenal discovery you've made?
So let me just come back to your last question. I'm told it's about 0.4 light years across, so that gives you some idea of the size. And in answer to your second question, I think it really depends who you ask. I'm sure Dr. Finkelstein and Dr. Batalha would have very different answers, and I probably would be closer to Dr. Batalha. So it really depends on what fields you work in. Everybody's sort of waiting for their particular observation to get done or to work on the data that's been taken in their particular area of interest. And I think part of the happiness of the science community right now is that, they're just getting to see what these observations look like and how this telescope's going to change the particular branch of astrophysics that they work in.
So do you have a favorite?
My favorite, I think, is still on the calendar to be observed over the next 6 months, which is the TRAPPIST-1 exoplanet system.
How about anyone else?
Can I make one point that I alluded to earlier? You're asking about the images, these beautiful images. Everything we know about almost everything we know about the universe is from the light we collect in our telescopes. And the great power of JWST is that it can take that light and spread it out into a rainbow. And in that rainbow, embedded inside of that, are these chemical fingerprints, evidence of motion, dynamics, all kinds of information embedded in that spectrum. So I would contend that the most profound images, if you will, are actually these plots of these graphical representations of the spectra, because they contain so many clues about the nature of the universe. So I love the images. I'm very inspired by the deep fields showing tens of thousands of galaxies, each with hundreds of billions of stars. And I look at that image and I wonder how much life is represented in that tiny little speck of grain of sand that's been imaged. But the spectra, I think, are extremely compelling, and I'm really looking forward to seeing more spectra so we can understand the diversity of all of the worlds that are out there.
So do you filter out all of the extraneous spectra and just get down to one particular wavelength or how do you do that?
No, the power is in looking at all of the colors. JWST is focusing on the infrared, but a very broad region of the infrared, and every single color tells us something different because the molecules that are out there in the atoms, they absorb each one with a unique chemical fingerprint, and each molecule tells you something different. In an exoplanet atmosphere, for example, each molecule's absorption happens in a different layer of the atmosphere. So if you look at many molecules together, you can build up the whole temperature pressure profile of that atmosphere. And you can start to understand things like climate and dynamics and really the history of that exoplanet, how it lived and how it has evolved.
Awesome. Okay, yield back.
Thank you very much. We're coming to a close. Dr. Babb and I would love to continue to talk about the infinite number of universes and the metaverse and dark energy and all that, but it sort of wanders away from our oversight responsibility, perhaps. I do have one more question, though. Who is Stefan and Stefan's quintet? Is that one of your children, too?
No. My other child is Kieran, who I think might be a future lawmaker, so you may see him here at some point.
All right, that's great. In the meantime, I'd have to say that of the 8 years that Dr. Babb and I have been on this committee, this is maybe tied with the gravitational waves hearing as the most fascinating that we've had. So you've been terrific witnesses. I'm really impressed with the depth of your knowledge and your excitement and your ability to transmit that to us and to the world. So thank you very, very much. So before, the record will remain open for 2 weeks for additional statements from the members or additional comments on the direction of history in the universe, and for any additional questions the committee may ask of the witnesses. The witnesses are excused, and the hearing is now adjourned.
Thank you, my friend. We'll get with you, though.